Hello everyone, good evening. Um, so how was quiz one? How did it go? Did it go well? That's good. Okay. All right. Okay, then let's start today's session. So we'll start with week five, and this week itself we will also have to do week six. So overall, there'll be trends from our side and 2 day sessions. We'll try to do both week five and week six, as week six deadline is also this Sunday, right? So we'll complete it this week. So has anyone gone through the lectures? Not at all. Um, mm. Okay, but I think week five is comparatively quite simpler as what we have seen till week four. I think week five is easier. We are starting with now the supervised algorithm. Okay, let me share my screen. Hold on, just taking some time to load.
Your screen is not visible.
Yeah, it's not loading. Just 1 minute. I'm trying. Give me 1 minute. Yeah. I don't know. Something went wrong. Just trying to see.
Ma'am, is it raining in your area?
Sorry. It's raining in my area. No, it's not raining.
Um,
Can you open it?
Network issue.
Yeah, I got it. I'll show. Yeah. Sorry for the delay. Okay. So let's start from week 5 content. So I will first brief you what all topics we have in week 5 and then we'll discuss those. So if you have not gone through the topics at all, it's okay. I mean, this session will give you some idea on what to expect when you're going through the lectures. So far we had been studying the unsupervised learning, right? But moving from forward from this week, we'll be switching to the supervised learning paradigm. So when we say supervised, what do we mean by that? We mean that when the data set that we have, it just not does have the feature, but it also have the labels associated with it, right? So uh, till week 4, what we have seen is that my data set look like x1, x2, x1, x2, so on till xn, right? This is how my data set look like, where each of these x's were features, and each of the x's were data point, and xi's were in RT. But now, when we're talking about the supervised learning, what we will say is that apart from these xis, we also have the labels with it. So we'll have y1, we'll have y2, so on till we'll have y1. Right? So now my data set looks like x1, y1, x2, y2, and so on. So this is what we mean by the supervised learning. Now, in supervised, in this course, we are going to study two different kinds of techniques. One is the classification, and the other is the regression. So we'll study these two topics in quite detail. Week 5 and week 6 is what covers the regression part. Okay, and week 7, 8, 9, 10 is where we study different kinds of classification algorithm. So these things we'll study in quite detail. Now, coming to classification problem and the regression problem, uh, like what kind of problem, like what do you understand by classification problem? So if you have certain tasks given to you and you want to, your task is basically to classify things into uh, certain classified into groups, 3 groups, and so on, right? So that is more like classification problem, and mostly we'll be studying the binary classification problem. So, for example, if you are given an email to identify whether if a new email comes in, whether you classify it as spam or non-spam. Yeah. So mostly we'll be studying with the binary classification problem. So when we say binary classification problems, my data set looks like this x1, y1, x2, y2, so on till xn, yn, where my xi's, though it is in RD, my features in RD, but my yi's can take only 2 values. So some places will take the labels as 0, 1, and some places we might take the label as minus 1, 1, depending on the kind of problems we are studying. Then, if it is not binary classification problem, it is we call. I mean, if the number of classes are more than 2, we'll call it as a multi-class classification problem where the labels can belong to maybe the YS can belong to 0, 1, 2, so on till k. Right. So this is something that has k plus 1 classes, or maybe is it a 1 to k we can say. So this is a multi-class classification problem where the labels vary from 1 to k. In this course, mostly we are not dealing with the multi-class classification problem. So we'll be focusing more on among all the weeks we'll be seeing this binary, like how to solve these binary classification problem. And once we understand that, we can extend the same idea to multi-class classification problem. Okay. I think some places there is multi-class, but most majorly it is binary class is what we are studying. Then in regression, what's the difference between this classification and the regression? So in classification, where our goal was to predict the classes, in regression, the labels. So if this is my data set, my labels now can take any continuous value, right? So yi will belong to R. So whenever we have to deal with such kind of problems where my labels can be in R, can take any values, then in that cases, such kind of problems will fall into the regression. Yes, Karan.
Ma'am, what about week 11, and do we have week 12 or is it Tuesday?
Okay, week 11 and week 12 is something apart from these techniques. So week 12, okay, I'll tell you. So some part of classification also goes to week 11, some part. And then we study more of the ensemble method and overfitting, underfitting. And then week 12 is the loss function and the neural network, some small introduction of a neural network, that's all. So yeah, that's the structure of the coming weeks. Yes, Ashish, you have any doubt?
Ma'am, you said that the difference between classification and regression is in regression the output belongs to real numbers. So in classification, can't we have output real?
No. See, classification. Like when you think of classification, right? So it's more like different classes you are going to put your object into, right? So as I mentioned, if you take the example of maybe object detection. So given an image, maybe if you have to predict whether the image is cat or a dog or maybe human, right? So you have to classify the objects, correct? Similarly, the spam classification problem, given an email, you have to predict whether an email is spam or non-spam. So here you have like a set of classes in which you want to put your data set into, right? Given a data point, given a feature to you, can you put that into a particular label, right? So you have a set of label with you, but in the regression problem, what do you have? Like very simple example from where we start with is, suppose you are given certain features of the houses and you want to predict the price of the houses based on those features. So you learn those features, and then you come up with an algorithm, and then based on that model, you given any new test data, you predict the price of the house, right? So what is the price here? Price here is a real number, real value, real number, right? So whenever your is like whenever your labels can take any continuous value, such kind of problems falls under the regression problem.
Okay, ma'am. So we are putting constraint in classification that the output should be only among this there is no constraint in regression.
Yeah, right. You can think in that way. Okay. So we'll start with the regression problem now. Let's see. So the very first thing, how does my data set look like? So as I mentioned, this is my data set. So x1, y1, x2, y2, so on to xn, yn. So this is my data set where I'm saying my x's is in RD and yi's belong to R. Right? So this is a structure, and we are also calling this our training data. Like if we are given a set of examples and we want to learn a model from there, so basically we're saying we're training our data and we're learning this model. So now what do we want to understand from here? Like if we are given the data set, what is our goal here? Okay, so we want to predict, we want to learn a map. So there's a function, this function, and we want to learn this function, which takes any input in any x in RB, and it gives us a real valued function. It's a real valued function, so it gives some value. So we want to learn this h. So we want to learn this h. So we want to learn this h, and how do we do that? How do we learn this? H is a question here. So let's say once we have this h here, let's say we fit the model and we have the h, but that doesn't stop there, right? So next, what we would be interested in is to know, let's say the h that we get after training. How do we check if this h is good enough, right? So we want to we want to try to understand that the h that we have is a good model that we have. So we want to check its goodness in a sense, right? So that can be done using this error function, and more specifically the squared error function. So we define a function which is squared error, and you can also call it a loss. So the loss. So the error of this h, the error of this function h that we have learned, we can define it as, so since this RD, the input will be xi, right? So, and this output is going to be what? It is going to be h of xi. So h of xi minus this yi, the true label. So yi's are the true label and h of xi is the learned label. Okay. So h of xi minus yi square. Okay, I is varying from 1 to 1. So we want to see how what is this error. So what is ideally that we would want? We would want that what model we have learned, it is giving is a very close approximation, or maybe the error we would want ideally to be 0, right? So the least we can go is that we can make the error to be 0, and once we have this error to be 0, we can say the h that we have learned here is a good model for our data set, right? But the problem with in most of the cases is when your h of xi becomes you will get the error to be 0 when h of xi exactly becomes equal to yi for every I, right? In that case, you will get the error to be 0. But in many cases, like when you're trying to make this training error to be 0, there's a very high possibility that your test error, if any new data set that you get, your test error can may not perform in the same way. So you can say your model has overfit. Okay, so this is if you're trying to make the error to be 0, it means this function h that you have, you can try to look into various spaces and we can have a function h, but then it will end up overfitting our data, which is something that we would not want. So currently, like in this week, what we are going to study is the linear regression, right? So we are going to restrict our space. So since we are allowing currently, let's say the whole space sigma to be like maybe the whole space of function. Okay, think of it as like we are allowing the whole all the functions which can be our edge. But now let's restrict it to specifically to the linear functions. Okay, so we'll restrict that and restrict the space of function, and we'll look at the set of all the linear functions, and we will allow those functions to be part of this. So like if we take this set of functions, so let's define this. So in the lecture we have used capital H. Let's stick to that. So now the set of functions that we had, which was H varying from RD, like mapping from RD to R. Now what we are saying is that we are looking at now a restricted space of function, and we'll call it as H linear. So H linear, here the set of functions that we will get. So let's, this is HW from RD to R, such that your HW of X, we're defining it in such a way such that HW of X is W transpose X for all W in R. Okay. So we'll restrict to this space. Alright. So now we are going to look for the functions only in this linear space of functions. So what is the updated problem that we have now? So we have the data set with us, and we want to learn this HW, which goes from RD to R. And our goal now would be to minimize this HW of Xi minus this yi, right? This true label. So again, this is the true label, this is the predicted label. So it's of HW of Xi minus yi square. I is varying from 1 to n. You minimize over W, which belongs to RD. Okay. So this is our goal. We want to minimize this error, or we want to minimize this loss, or something. So we want to minimize it, basically. Kiran, you have anything?
Yes, ma'am. Instead of taking like a squared error, why can't we take absolute?
Okay, so one problem that happens when you take the absolute error is not differentiable, right? Your absolute function.
Okay.
Ma'am, can I ask something?
Rohit, you have any questions?
Yeah.
Yes.
Ma'am, I didn't understand overfitting. What's an overfitting?
Okay, so overfitting. Overfitting we'll see in more detail in week 11. But just to understand here, maybe you can think of it as something where, let's say, for this data set that we have, let's say this is the model that we get. Like for this training data, we got this model H. Okay. Now, what is happening is, like, we have fit the model to this extreme that my error is coming out to be 0, right? So error is coming out to be 0, and in many of the cases, quite possible that on training data, whenever you are able to make the training error to be 0, but the same model, the same H, if you take it for the test data, if it is not working in the same way. So suppose if you are getting the error to be 0 on the training data, then you would expect that for the same model H, if you are given some new data to you, that is test data, it should perform equally well, right? But if that doesn't happen, it means we can that is that if your model is making the error to be very less on the training, but it is not performing the same on the test, that is if the error is going quite high, then we can say your model has overfit.
Got it.
Okay, so we would not want to do that.
Ma'am, is it something like up until some point, as in when we keep adding more data, the accuracy increases, and beyond some point, the accuracy start decreasing. So that volume of data, can we say that we are actually overfitting the model, and more data adding means it will not perform any better?
Yeah, we can say that. So after a certain point, like even let's say even if you take the same edge, maybe for a certain time your test error is also reducing, but you will come to a point where you will see a sharp jump in the error, right? I mean, it will just after a point it will shoot up. So
What is the cause of that behavior actually? More data should be actually better decision making, right? But why adding more data, the model actually start degrading? I mean, what is the reasoning behind that? Why does it perform that way? Uh,
okay, we'll see all that in week 11 when we go. Okay. So
okay.
we have not we have not introduced overfitting at all currently. So let's not discuss more on that part right now. So we'll stick to regression. Yes.
Ma'am, we are discussing about the function h now. So we are giving it training data and we are predicting it. But how is it learning from that data? Training.
Yes. So how is it learning from the data? So again, we'll do the training, and how is it actually working? We can't see it here, but what we are saying is now we are restricting this h. I mean, the set of functions or uh, this like all the functions that we can consider for h is the linear function, and that we have defined as w transpose x, right? So now like this very simplest linear model we're looking at. So w transpose x is the set of function that we're looking at. So now what we have is we have these xi's with us, which is the training data. We have these xi's, but w is something we don't have, right? So we will learn that. I mean, I'll come to it. So there is a proof for that, and we'll see what is the ideal w that would be a best choice for our model. Okay, we'll come to that. Okay. Right. So this is our goal now. So we want to minimize this. We want to minimize this loss, or we want to minimize this error. So how do we define this HW of xi? We defined this HW of xi to be W transpose x, right? So we can write this as sum over W transpose xi minus yi whole square, where I is varying from 1 to n. So we want to minimize this. Now we can also write like this is this is for each vector we have written this, right? In shorthand notation, what we can also write this as, or in the matrix form to say, we can write this as that this is going to be equivalent to norm of my x transpose w minus y whole square. Okay. So this is L2 norm that we are taking. And what is this matrix x here? The matrix x that we are considering is this column vector. So we have this x1, we have this x2, so on we have this xn. So this is going to be a D cross N matrix. Right? What is my W? W belongs to RD. So W1, W2, so on to WD. This is my D cross 1. What is going to be Y? y is y1, y2, so on till yn.
Constant.
Constant. So instead of so what we said is, instead of doing this, which is minimizing sum over W transpose xi minus yi whole square, where I is varying from 1 to n, or y, we can instead do minimize my x transpose W minus y. So we'll solve for this problem. Now this is nothing but an unconstrained optimization problem for us, and we know how to solve any optimization problem. So how, like, from where did we start? We started with the data set that we have, x1, x2, so on to xn. And we saw that the kind of functions that we want to learn are the linear functions. And we defined it as set of all h such that it takes a value for any xi, W transpose xi. And our goal is to minimize this squared loss. Okay. And in matrix notation, we can write this as norm of x transpose W minus y squared. So this is nothing but an optimization problem, an unconstrained optimization problem, and we know how to solve this unconstrained optimization problem, right? So what do we do here? Anyone want to guess? Like, how do you do this?
Find the minima by differentiating.
Yeah, find the derivative and differentiate it, right? And then we set it to 0 and we get our W from there. So this x transpose W minus y, we know we can write this as x transpose W minus y transpose, x transpose W minus y, right? This is nothing but, I mean, to remember, if let's say W is any vector, I can write this as norm of this as W transpose W. So in this case, we have this x transpose W minus y. So we can write x transpose W minus y transpose, x transpose W minus y, right? Let's solve for this. What do you get? So you get x transpose, so you get W transpose x minus y transpose, x transpose W minus y, right? So what is this? This is W transpose x, x transpose W, minus W transpose xy minus W transpose x transpose W plus y transpose, right? This is what we have. So what do we want to do next? We want to take this derivative. So let's call this f of W, because this is a function of W. Now, if you take the derivative, and what do we have to do? We have to set it to 0. So take the derivative. What we will get from the first term is that this is equivalent to 2 times xx transpose W. Okay. Plus, if you look at the last term, this does not have the W in it. This term does not have the W, so this goes to 0. And let's look at the second and the third term. So the second term is like, what does it say? It says W transpose xy, right? And what can you write this as? We can write this as x of y transpose W, right? And this is nothing but W transpose xy, right? So this two term combined can become minus of 2 W transpose xy. Okay. So if you take the derivative of this term with respect to W now, it becomes minus of 2 xy. Okay. Now you set it to 0. What do you get? You get xx transpose W is equal to xy. So we can say this W is nothing but XX transpose inverse. XX. So this is the W that we get from by solving this problem. So we can call this as W star to be XX transpose inverse XL. Yes, was there Rohit?
Ma'am, I want to start something. Ma'am, how you wrote 2 into x transpose w?
2 into
The first term, w transpose into x transpose w. How did you simplify this?
okay. So see, you have this is f of W that we have, right? This one. Now what we want to do, we want to take its derivative. Okay. So now instead of derivative, we'll have to take the gradient, right? Yeah. So think of it as, see, this x term does not have the W in it. So what do you have? You have more like W transpose W with you. Think of it as a star. Okay.
As a variable, as a
what?
constant.
So W transpose W, okay? You have to take its derivative. So maybe you can think of it as W transpose W as W square, all right? So what happens if you take the derivative of W square? It becomes 2 times W.
Yeah.
Yeah? But I mean, it's not, doing this derivative is not that straightforward. There is a, I mean, there's a step-by-step process through which you can come through it, which takes a little longer time. Okay, but if you can understand it in this way, like W transpose W, you can think of it as square, and then it becomes just 2 times W. Okay.
Ma'am, is
But you
that
can,
there in lectures?
it's not there in lecture completely, but I mean, vector calculus is again a separate topic that we'll have to look at.
Okay.
So okay, what I can do is let me. Whenever we meet next, I can just take this part. I think it will be useful for us, useful to you later as well. So I will take the. I'll take maybe half an hour for you to understand this vector calculus. Okay. So for now, you just remember this.
Okay, ma'am. Ma'am, and how did you converted the third term, y transpose into x transpose into w?
Okay, see, you can, this is Y transpose X transpose W, right? So this is what Y transpose X transpose
X
you can
whole transpose, yeah.
a whole transpose,
Mhm.
right? Now this is you can treat it as one, maybe
Okay.
think of it as one or some one matrix,
Okay.
and it is more like some A dot A transpose B,
Okay.
right? So this you can write as B transpose A as well, right?
B transpose A in of whole transpose, no?
No. I'm saying XY, you call it A. Okay? Then W, you call it B. All right. So what do you have? You have A transpose B. You can write this as B transpose A as well.
How, ma'am?
That's when we get scalar, right?
Where is your X? X is in T cross N.
Yeah.
Where is your Y? N cross 1. Where will be your XY?
D cross 1.
D cross 1. So it is a vector.
Hmm.
Can I call this maybe let's call it a vector A, which is
Yeah.
in D cross 1.
Yeah.
Then you have a W. Where is it? D cross 1. I'm saying calling it as a B, which is in D cross 1.
Okay.
This is what? This is one vector. This is another vector. How do you take the dot product? I mean, now what is A is A1, A2, so on till AD. What is this B? B is this B1, B2, so on till BD. if you do A dot B, which is A transpose B,
Mhm.
right? What is it going to be? A1 B1 plus 1 to AB BD.
Yeah.
What is going to be B transpose A?
Oh,
Same.
yeah. B dot A.
So that's what we did.
Okay.
So XY transpose W, we can just write as W transpose XY. Okay.
Okay.
And this matches with the second term. So they both are basically the same. So that's why we are able to write this. So we are able to write minus of W transpose XY minus of Y transpose X transpose W to be minus 2 times W transpose XY. And now if we take its derivative with respect to W, we just get minus 2 of XY. So we solve for it and we get our W. So this is the W that we get for the linear regression problem. All right. Okay. Let's move. Yes, Kaushik.
Like in the lecture, sir discuss about the pseudo inverse. So can you briefly explain that? What is pseudo inverse?
Okay. Let's see. Why pseudo inverse has been brought is maybe your XX transpose is not invertible. Then in that case, you cannot do the inverse. So there is this separate topic again. So in that case, if you can't find the inverse, you do the pseudo inverse. So that's why in general, in the lecture, pseudo inverse has been used. That's the only reason. But for simplicity, we can like take it as inverse. Let's just suppose that the inverse exists and we can move ahead. Again, pseudo inverse is a very separate topic, which will take another some time.
Okay. Basically, ma'am, for some if XX transpose is not invertible, then we
Then
use
we can use the pseudo inverse and we can proceed. But let's just assume we have the inverse exists and we can do this XX transpose inverse. So this is the solution that we get.
okay, got it. Thanks.
Right. So this is a solution that we get for this linear regression problem. Now, so if W star is the solution for this problem, which is like you wanted to solve min W transpose or specific then of X transpose W minus Y, right? The norm. Yes. So we wanted to solve this, and the solution we get is this W star. So the question now is like how does this like where does this W star lie, right? Or what does it mean to say that the star is my XX transpose inverse XY? Yes, Kiran, that's correct. Okay. So before we go to this geometrical view of this linear regression problem, we can look at some computational part, like what are the problems that we can face while we try to get this W, right? So see, uh, what did we get the solution as? The solution we get is W star to be XX transpose inverse XY, right? And where does this X lie? X is in X is in D cross N. X transpose is going to be N cross D. So this matrix that you have, which is XX transpose, this is basically going to be a D cross D matrix, right? And what you have to do now is to take its inverse, right? So if you want to take this inverse, and let's say the number of dimension, if D is quite large, let's say if D is quite large, okay, then computing this inverse is going to be very time consuming, right? So that is something that we would want to avoid. Okay, so to deal with this situation, where when the number of dimensions can be when the number of dimension is quite large, which makes the computation very expensive, we can follow this technique, which is gradient descent. Right? I hope many of you would have already heard this, heard about gradient descent, or would have studied in some courses already. So, what does gradient descent do here? Does anyone know what does gradient descent do? Mhm.
It measures the contours,
It measures
the rate of change of contours.
okay. What is the update rule of gradient descent? Hmm?
Ma'am, that W t plus 1 is equals to W t minus uh, that
Some
some
unique
step
group.
size
Mhm. Step side, yeah.
and something in multiply.
Mm.
The gradient of
The
f.
gradient.
Yeah. So, what is the update rule for the gradient descent? Okay. Are you able to see my screen?
Yes, ma'am.
If I'm annotating on the screen, can you see the green one?
Yes, ma'am.
Okay. Okay. All right. Um. All right.
The
So
screen
what?
caption is not correct.
Ma'am, can you please close that? This is saying no. This version of OneNote will reach support.
Yeah. Yeah. I'm get closed. Hold on. Something went wrong again. One minute, let me take one. Okay, I'm not able to open the screen. Um,
But you can use online editor.
okay, let me do one thing. Wednesday, does anytime, if I schedule another 1 hour, 1.5 hour session on Wednesday, does it work for you?
Yes, ma'am.
Uh, okay, so maybe 6 o'clock or 7 o'clock, I will schedule 1 hour session on Wednesday. So whatever, I mean, we have covered like 40% today, and the remaining is still left. So we can do that part on Wednesday if that works for you all.
At 6, ma'am.
Uh, Either 6 or 7. Anyone has any session on Wednesday?
No, ma'am.
No, no.
So Wednesday you don't have a session. Okay. So okay, I will do one thing. I'll schedule one session for 1 hour on Wednesday, and we'll finish this, and then we'll continue for the other weeks as well.
Ma'am, what we'll discuss on Friday session?
Okay. So see, Friday session we'll discuss more on week 5. Like we'll solve some problems from week 5, and we'll also start with the week 6 concepts. As your week 6 deadline is coming on Sunday, so we'll also cover that. So Friday session will be week 5 plus week 6. So week 5 problems plus week 6 theory, and Sunday session will be week 6 problems. And if something from the theory left, we'll do it on Sunday. Thursday is going to be week 5, your activity practice plus the programming part, and Saturday is going to be week 6, AQ, PQ, PA plus programming part. So that's the agenda for this week.
Okay.
speak of this for the session. Okay. All right. So really sorry for this. I don't know what is going wrong with my system. So we'll schedule on Wednesday one session, and we'll close this for now. Okay. Thank you,
Yeah,
everyone.
okay, ma'am. Yeah, thank you.
You can drop off. Okay. Thank you.
Yeah, thanks.
Thank you, ma'am.
Thank you. Thank you, everyone.
Hello.